All right, and welcome back. So today we are going to be talking about how to multiply and divide radical expressions. The reason that we're talking about this now is because previously we talked about how to multiply polynomials. And it's going to be a very similar concept, but we have to think about the rules and the properties of these radical expressions when it comes to multiplying. Dividing, we're going to be talking about a whole new topic. So without further ado, have out those guided notes and let's start. So we're going to use the product and quotient properties to multiply and divide radical expressions. So let's just review what those are. The product property of square roots or of radical expressions is if we have the square root of a times b, well, we can break that up and have the square root of a times the square root of b. Similarly, with the quotient property of square roots, if we have the square root of a divided by b, well, we can break that up as the square root of a divided by the square root of b. We are going to be using these ideas to help us multiply and divide radicals. We're going to be having them for two separate to go into one big radical or one big square root. So let's talk about an example. Let's multiply the square root of 6 by the square root of 10. Now we can't simplify the square root of 6 and we can't simplify the square root of 10. So these currently are simplified, but we're going to multiply these two values. We're going to use a product property where we're going to take the square root of 6 times the square root of 10. We're going to put them both multiplying with each other underneath one square root. So we have the square root of 6 times 10. We know that 6 times 10 is 60. So we multiply those factors underneath the radical. We call that the radicand. And now we're going to simplify the square root of 60. Now you can do whichever method you like. You can use the perfect square properties and think about, okay, what perfect square goes into 60? Or you can use the idea of breaking 60 down and pulling out those pairs. So if we're using the perfect square factor, we know 4 times 15 is 60. We can break it apart again down the square root of 4 times the square root of 15. And we know the square root of 4 is 2. So therefore, the answer here is going to be 2 square root of 15. Awesome. Let's talk about another example. This one is on the right-hand side of your guided notes. It says a quotient with a square root in the denominator is not simplified. We're going to do something called rationalize the denominator by multiplying by a form of 1 to get a perfect square. Essentially, if we have a fraction, and in that denominator, there is a square root, there's a radical, that is no bueno. That is not fully simplified. We want to get a whole number in the denominator. So to do that, we're going to multiply both the top and the bottom, the numerator and the denominator, by the square root in the denominator. But let's talk about an example, that way we can go through together. Let's say we want to simplify the square root of 10 divided by 3. We are going to be using the quotient property and we're going to break it apart. So now it turns into the square root of 10 divided by the square root of 3. This is not simplified because we have a square root in the denominator. So to undo that, we're going to multiply both the numerator and the denominator by the square root of 3. Now we're allowed to do this because we're only really multiplying by 1. Here is what I mean by that. We're multiplying by the square root of 3 divided by the square root of 3. Well, anything divided by itself is 1. So we're not changing the overall value, we're just changing a little bit how it looks. Now we can multiply the square root of 10 times the square root of 3, so square root of 30. The square root of 3 times the square root of 3 is the square root of 9. And we know the square root of 9 is 3. So our final answer becomes the square root of 30 divided by positive and whole 3. We can't simplify the square root of 30. If we could, we would. But now that we have a whole number in the denominator, we are A-OK. With this, please work on problems 1 through 6 on the guided notes and resume when you're ready to move forward. All right, so now we're looking on the back side of your guided notes. So we have terms can be multiplied and divided if they are both under the radicals or if they are both outside the radicals. So if we have this expression, we have 5 root 2 times 4 root 3. You're going to notice that we're going to multiply 5 and 4 because both the 5 and the 4 are on the outside of our radicals. We're going to multiply root 2 by root 3 because those are underneath the radicals. When we do that, 5 times 4 is 20. Square root of 2 times the square root of 3 is a square root of 6. So if the numbers are outside the radicals, we can multiply them, technically, and divide. If the numbers are inside the radicals, we can multiply and divide them. But we can't multiply a number on the outside with a number on the inside. We can't do that. If the numbers on the outside, they can be operated on. If the numbers are on the inside, they can be operated on together. But we can't crisscross. All right? Awesome. Cool. Let's go through an example of where we really connect with polynomials and how we multiply polynomials. Let's say we want to multiply the square root of 3 by 6 plus the square root of 8. We want that to be in simplest form. So we start out with our original problem. If this was just a polynomial, let's say this was x times 6 plus x. Well, we know we're going to be distributing. So we're going to distribute this root 3 to 6, and we're going to distribute root 3 to root 8. That's what it formally looks like when we distribute. Notice how we have square root of 6, or square root of 3 times 6 in red underlined, and the square root of 3 times the square root of 8 in the green underlined, because we distributed. And now we're going to simplify. Well, we can't do anything with the root 3 times 6 because one number is on the outside, one number is on the inside. So it stays as 6 root 3. But we can multiply the square root of 3 and the square root of 8 because both numbers are underneath the radical. Therefore, we end up with the square root of 24. And we can factor the square root of 24. So all we're doing here is we are factoring the square root of 24. Whichever method you like to. In this example, we went through the perfect square factoring because that, to me, I think is the easiest way, especially when our numbers are smaller. But all we need to do is just make sure we fully simplify. And now we can't add those together because we don't have the same square root. So our final answer is 6 root 3 plus 2 root 6. Awesome. Awesome. Now we can also use the FOIL method to multiply binomials with square roots. And again, we're going to be going through an example, but that's why we talk about multiplying polynomials first, because now that we have some practice with it, we can apply that same concept to multiplying expressions that have a radical. So let's say we want to multiply 3 plus the square root of 2 times 4 plus the square root of 2. Well, we're going to write our problem first, and now we're going to use the foiling method. Remember, the FOIL stands for first, outside, inner, and last, FOIL. So we're going to multiply the first terms, so 3 and 4. Multiply terms on the outside, 3 and root 2. The terms on the inside, root 2 and 4. And whatever is last, root 2 and root 2. So we show that it is done out here. I'm just going to connect our colors together. So 3 times 4 was in red. 3 root 2 was in green. 4 root 2 was in blue. And 2 root 2 times 2 root 2 was in purple. We're going to simplify any way we can. So first we're going to multiply. Let's highlight what was done. We multiplied 3 times 4. And we multiplied the square root of 2 times the square root of 2. We can simplify. The square root of 4 is 2. And now we have some like terms here. We have like terms. Let me show that. We have like terms. 3 root 2 plus 4 root 2 That's 7 root 2. So we can combine like terms if we have them. Sometimes we won't, but sometimes we will. So whenever we can, we always want to simplify and combine those like terms whenever possible. Awesome job, kiddos. With this, please work on problems 7 through 10 on the guided notes. You're doing really, really well. Let me know if you have any questions at all. You're doing a fantastic job. Let me know if you have any questions, and I'll talk to y'all soon. Have a good one.